Here we go on chapter 2, going over chemistry and molecules of life. So just to give you an idea of where we are in the class, going back to kind of our intro PowerPoint, we're starting unit 2. So we've gone from sustainability and our word was malama, and now we're moving into the cells part of the class. So we're moving into the kalo patch or the lo'i. And this is where we're going to be learning more about the very basics of cells. So the chemistry, the nutrition, photosynthesis, respiration, all of that good stuff. So you can see here, we're going over chapter 2 through chapter 6, and that's what you'll be responsible for in unit 2. Okay. So learning objectives, what you should get from this lecture. You should be able to list and give examples of the 5 functional traits shared by all living organisms. Know that all matter is made of elements. Understand how carbon is one of the most versatile molecules. List the 4 molecules of life and explain the properties and characteristics of water, including how to measure pH of solutions, which is part of what your class activity will go over as well. When you're reading through your chapter, you will get a lot about Mars. So the chapter focuses on the chemistry of life and on our mission to Mars, prospecting for life on the red planet. Mars is obviously one of the planets that we think has the greatest potential for life, and seems the most similar arguably to Earth than any of the other planets that we've currently found. So when we're going through looking for life on different planets, there's a couple things, or there's 5 things really, that we're looking for that characterize what life is. Keep in mind that these 5 functional traits that we've come up with as scientists are based only on life on Earth. So life on Mars or any other planet might look a little bit different, but for life on Earth at the very least, we're going to characterize it by these 5 functional traits. The first is growth, and growth basically is any increase in size after reproduction. So you either have to grow in size or in cell numbers, whatever it is, you have to grow to be alive. The second is reproduction. So you have to have offspring and they have to be viable as well, right? So the offspring might be similar to you, or they are similar to you, but they're not identical, and their siblings are going to be similar to each other, but also not identical. Homeostasis is the third one. So homeostasis is just being able to maintain a stable internal environment despite any changes that you might have in the external environment. So being able to keep your temperature the same, your pH, or not necessarily the same, but within a range that's acceptable for your body. So humans are a little bit different than, let's say, whales or raccoons or whatever it is. The fourth is you have to be able to sense and respond to stimuli. There's lots of different ways that you can do this as a living thing, but let's say that you move towards food or you move away from a predator. It doesn't have to be movement, though. You might not be necessarily moving something. You might be using one of your other senses, or responding in some different way. So keep in mind that this doesn't mean that you're moving necessarily. It just means that you can sense and respond to the stimuli presented in the environment. And last but not least, you have to be able to obtain and use energy. So usually we're obtaining energy from food unless you're able to go through photosynthesis, which we'll talk about in a few chapters. And then you have to be able to use that energy through different chemical reactions that convert that energy into something that's usable. So converting that food energy into kinetic energy where you go running or something similar to that. So these are the 5 functional traits of all living things. You can't just have 1 or 2, you have to have all 5 to be considered living. So please make sure that you know these really well for quizzes, exams, everything. Okay, so is a virus a living thing? So let's talk about let's start with what do we know about viruses? So viruses are a little bit weird, and this is super debated amongst scientists about whether they're living or not. They almost seem like they're living because they can kind of evolve and they can transfer from person to person. But remember our 5 functional traits, right? So you have to be able to grow, which viruses can pretty much do. You have to be able to reproduce, which they can do, but keep in mind, how are they doing these things? How are they growing and how are they reproducing? They have to have a host to be able to do these things, right? So they're not able to do it on their own, which is kind of a problem, if you ask me, in terms of considering it what if it's a living thing. And then maintaining homeostasis, sensing and responding to stimuli, obtaining and using energy, doesn't necessarily do any of these things on its own. Again, it's pretty much depending on a host. The other thing about viruses is that they can reproduce and pass their genetic information on to new viruses, right? But they're not made of cells, which is interesting. And we haven't gone over cell theory yet, but cell theory basically says that all living things are made of cells. So based on that, I would argue viruses are not really a living thing, but there are scientists that would argue otherwise. All living things made of cells. So that's cell theory. Instead, viruses basically are made up of a protein shell that has the genetic information inside. Okay, and then they again reproduce by infecting a host cell, and then they hijack things that are in the host. They hijack all of their cells, and then they start manufacturing their own information. So I would argue they're probably not living, and for those reasons, they're not made of cells. They're made out of some genetic information encased in protein, and they require a host. So all of those things, I would argue, make it that they're not living. But if you want to argue the opposite end of the coin, feel free. So viruses and other things like prions, which are just infectious proteins, um, that are responsible for a couple different things like mad cow and mad cow disease and a few other related illnesses. But these kind of things defy what our definition of being alive is, because they seem like they're alive and well, right? Like we would probably want to argue that COVID-19 is alive right now. But based on those 5 traits and cell theory, probably not. But again, prions that are responsible for mad cow disease are basically proteins, and they're not contagious unless you handle the CNS. So they aren't contagious just passing around, unless they're kind of the same with COVID, right? COVID, you have to inhale it through your respiratory system or your eyes. It's not usually just like if you touch something on your hand, it's going to work its way into your body. So again, it's kind of a weird life. It defies our definition of being alive to some extent, but it doesn't quite fit everything. The other thing that's a little bit strange are these things called extremophiles, which we'll talk about a little bit more in a few chapters. But extremophiles basically do exactly what they sound like. They live in really extreme environments. So really extreme pH levels, really extreme temperatures, pressures, like if they're living at really high altitudes or really deep depths in the ocean. These guys also kind of defy what we think life would normally look like. So that's a little bit about life on Earth. And again, that's based on life on Earth. So those 5 traits and cell theory, that might change if we find something on another planet somewhere in the universe. We're basing that on Earth, which is a carbon-based planet, carbon-based life forms, which we'll talk about in a second. So that might change a little bit. So now we're going to kind of back it up and go to our building blocks, right? So now we're starting at our smallest unit of matter, which is an atom. Atom means that it can't be broken down chemically. It's the smallest unit of matter you can possibly have. It doesn't mean it's alive or not living. It could be either of those. And then the next step up is an element. So this usually has, well, not usually, it always has only one type of atom, but it might have multiple atoms, right? So it's not the smallest. It does have distinct chemical properties. So it's things like hydrogen, oxygen, iron, magnesium, copper, all of those are elements, right? So they're made up of only one type of atom, although there could be several atoms within that element. And then these elements, right, or atoms can join together and bond chemically to form a molecule. So say we take hydrogen and oxygen, we can bond those together to create water or H2O, and that's a molecule. So our atoms, our smallest units, are made up of protons, neutrons, and electrons. You guys have probably heard this, especially in like chemistry. So protons are our red guys, our positive guys in the nucleus. Neutrons also hang out in the nucleus with these guys, and they are neutral, just like neutron, neutral. And then our electrons are negative, and they orbit around these in these different rings around the nucleus. So when you're joining these atoms together to create molecules, they're joined through something called covalent bonds. So covalent bonds occur when atoms share a pair of electrons. Okay, so we've got nitrogen here in the middle, this big guy, right? And then we've got 3 hydrogen atoms over here. So we want to join them together, and they're going to create these covalent bonds, which are fairly stable. And in order to do that, they want to fill these orbits. These are the orbits, right, that have the electrons. So the first orbit can only hold 2 electrons, but the second one and above can usually hold 8. So you can see we've got 1, 2, 3, 4, 5 on this nitrogen, and we've got 3 hydrogen molecules that want to bond to this nitrogen. So when they bond, these electrons are basically being pulled in here, and then they're going to become super stable and pair up essentially. Okay. So that's how these covalent bonds form. And there's different kinds of bonds. It's not just covalent bonds. We also have hydrogen bonding, which is a little bit less stable, and a few other bonds, which we won't really get into this semester. But like I said, carbon is the basis for life. It's essential for, or at least for life on Earth. It's essential for life, and it can make up to 4 covalent bonds, which is the max. So it's got 4 electrons in its second shell, which means it can make 4 covalent bonds, a total of 8 electrons. That's super stable, right? So you could see with that NH3 molecule that we just made before, it had 3 hydrogens bound to it, but it still had an extra 2 electrons over here. So it's like pretty stable, but not completely stable. This guy, carbon, can make those 4 covalent bonds, which are really strong, really stable, and there's no other electrons that are even tempted to bond with any other sort of atom. Okay. There's only 6 elements that make up most of humans' weight, so a little under 99% of our weight. Oxygen is the biggest one, it's about 65%. Carbon is second at about 18%. Then we have hydrogen, nitrogen, calcium, and phosphorus, and there's a bunch of other stuff in really small amounts, but carbon and oxygen are the biggest ones, carbon being one of the main ones and why we refer to ourselves as carbon-based life forms. So again, we'll get into what organic is versus not organic. But basically, organic molecules have carbon atoms, and they covalently bond to carbon and hydrogen. So organic versus inorganic. This isn't, when we're talking about it in this way, it isn't like what you see at the store, like I'm going to buy organic raspberries versus inorganic raspberries. Organic is basically living versus inorganic, which is non-living. And that's not a direct translation, but generally that's kind of how you can think about it. So organic molecules, they have to have a carbon-based backbone and at least 1 carbon-hydrogen bond. So these guys definitely have carbon, but if I ask you in, say, a quiz or test question, what makes an organic molecule? The thing that they have to have is a carbon-hydrogen bond. Okay, so keep that in mind. They've got to have, or you can refer to it as a hydrogen-carbon bond. Either way, it's the same thing. They have to have that. Inorganic molecules might still have carbon, probably do have carbon, but they lack that carbon-based backbone. So they do not have any of those hydrogen-carbon bonds. Okay, so that's the difference between organic and inorganic here. So again, organic, they have carbon, but they have to have that carbon-hydrogen bond. Okay, so for molecules of life, we've got something called macromolecules, which we'll get into in a little bit too when we start talking about nutrition as well. But macromolecules are just large organic molecules, so they have that carbon-hydrogen bond, and they're composed of subunits called monomers. So anytime you see mono in something, right, mono means one. So monomers link together to form polymers. So poly means more than one, multiple, right? So they form these polymer chains. So basically it's just little units, like say this is a monomer, it's going to link up with its other monomers and form these big chains to create these macromolecules. So we've got 4 types of complex macromolecules that make up living things. The first is carbohydrates. Again, this is something you're going to want to know, our 4 main macromolecules that make up life. Carbohydrates, proteins, lipids, or fats. You can also refer to these as fats. I mean, if you see this on a quiz or test, you're going to want to call it lipids, but they're also known as fats, and nucleic acids. So let's go over them a little bit here. Again, you'll see a little bit more once we get into nutrition, but carbohydrates. So carbohydrates are made up of sugar monomers. And usually when we talk about sugar, not always, we're talking about glucose, right? And glucose is a monosaccharide. So saccharide just refers to a sugar, mono again meaning one. So glucose is basically one sugar molecule. So it's a sugar monomer. So these sugar monomers, or let's say glucose molecules, all link together to form a polymer chain, and that's when we can make something called a complex carbohydrate. So over here we have simple, and then we get more complex carbohydrates over here once they start linking together to form polymers. Okay, so we have simple carbohydrates. These are just like they sound, they're simple, right? So these are things that can be broken down into glucose, which is our one main molecule, and we can use for energy. So these usually don't have very much nutritional value. They are made by green plants, but examples of simple carbohydrates are usually things that you like kind of want to avoid, or at least you want to avoid in large quantities, and we'll get into that in nutrition. But things like soft drinks, sugar, milk, fruit, again, not all of these are necessarily bad, but you usually don't want to have too much of them, right? Versus complex carbohydrates, still made by green plants, still broken down into glucose for energy, but they're complex, so it takes a little bit longer to break down. They usually contain more fiber, they keep your digestive system nice and healthy, they make you feel full a lot longer, which makes sense, right? If you think about drinking like a soft drink or eating a bunch of sugar versus eating something like vegetables or oat bran, corn, peas, whole wheat bread, all of those are examples of complex carbohydrates. Next up, we have proteins. So proteins are made up of something called amino acid monomers. So again, monomer is just one unit, right? Amino acids are something we'll talk about a little bit more in detail here coming up. But we have little amino groups that form together and again can form into these polymer chains. We can make a whole linear strand of amino acids, and there's different side chains that we can make, and these make up proteins. So proteins have a certain shape to them that they will bundle into, but they're all at the basis of them made up of these amino acids. Okay, so remember that. We'll get into that a little bit more once we get into DNA and stuff too in Unit 3. But proteins are made up of amino acids. Okay. And last but not least, we have nucleic acids. These are made up of nucleotide monomers. Again, we'll get into this more with DNA and RNA in Unit 3. But basically, we have a nucleotide, which has a sugar and a carbon group over here, a phosphorus carbon group, and then a base attached to it. So there's 4 different types of nucleotides. You won't need to know them until Unit 3, but these make up your RNA and DNA in your body, which is your genetic information. Okay. And then last, I think I said nucleic acids were last, but I forgot about our lipids. So lipids are actually our last ones. These are made up of fatty acids. Usually when you think of lipids, you think of different kinds of fats or sterols. And basically, they're just really, really long chains of carbon atoms that are bonded to one another, and then also to hydrogen atoms. So these are basically just big chains of carbon-hydrogen bonds, and it's just repeating and repeating and repeating. And these are our fatty acids. Okay. They're saturated versus unsaturated. Again, we'll get into a little bit more once we get into nutrition, but these are the main four molecules of life. Okay, so we have the lipids, the nucleic acids, the proteins, and the carbohydrates. So when we're looking at a cell, that's our basic structural unit of life. So we just looked at matter, right? We started with the smallest base of matter, which is an atom. That makes up everything, all matter. Living, non-living, whatever it is, that's the basics. But once we start getting to living things, the basic structural unit of life, now we're talking about the cell. All cells have the same basic architecture, okay? So they're all water-based on the interior, and it's separated by something called a cell membrane. Okay, so in the cell membrane, so we've got a bunch of basically water inside that allows different molecules to dissolve in and out of the cell. And it's surrounded by the cell membrane, which sometimes you'll hear called a phospholipid cell membrane or semi-permeable cell membrane. But it's made up of these things called phospholipids, right? Remember, lipid is our fats, the ones that we just talked about. So we have a water-loving head, which is hydrophilic, and a water-fearing tail, which is hydrophobic. So in our phospholipid bilayer of our membrane, we have the heads here facing the outside because they like water. So they can face the inside of the cell where we have water touching them, and they can face the outside of the cell where we have water touching them. Whereas the water-fearing tails, the hydrophobic tails, are in the middle and aren't really exposed to as much liquid. That's where we have different proteins and things making their way into the cell, essentially. Okay, so this lipid bilayer is just separating water inside from the outside of the cell. And we'll get more into that in this unit as we talk a little bit more about it. But water, as you know, is essential for life, right? And there's a few different reasons why we consider it essential. You can go weeks without food, but you can only go days without water. So there's a few different reasons why it's essential. The first reason, property number one, why water is essential for life, is it's what's called a universal solvent. All of life's chemical reactions take place in water, and a lot of living things, again, can only survive a few days without it. So when we're talking about a solvent is a substance in which other substances can dissolve. So let's say that you have a protein powder. Okay, you're going to make a protein shake. And I know you can put it with almond milk or whatever, but let's just say that you're going to mix it with water. The water is the solvent. The protein shake or the protein powder that you're using are solutes. So you're placing solutes into a solvent to dissolve them. Okay. Same thing with like if you're making emergency or even if you're just dissolving salt and water, right? The solvent is the water, it's the substance in which you're going to dissolve the other stuff. So again, it's transporting these dissolved molecules, which are the solutes, say like your protein powder or your emergency or your salt, and it's putting it into that solvent, the water in this case, and making it into what's called a solution. So the solution would be your protein shake, or it would be your emergency drink, or it would be your salt water. All of those things are solutions that you've created by dissolving a solute into a solvent. Hopefully that makes sense. I know it's a lot of very similar words and vocab thrown at you in one time. So why is water such a good solvent? And when we say it's a universal solvent, I don't mean that it dissolves absolutely everything, right? You can put some stuff in water, like say oil, which isn't really a solute, right? But water and oil don't mix. There's some things that won't dissolve in water, and that's okay. Universal solvent means that most things will dissolve in water. And the reason why it's such a good solvent is it's something that we call polar. So basically you have a more positively charged side and a more negatively charged side of water. So on our hydrogen end, where we have our two little hydrogens, that's a little bit more positive. And then the oxygen is this big negative molecule. So we've got a more negatively charged oxygen side. So it doesn't share the electrons equally between the atoms and between these covalent bonds, which means that it's really good at attracting things to either its positive or negative end, kind of like a magnet, which means that it's able to dissolve these other solutes. Okay. So when you're looking at something like salt, if we want to make salt water, right? So we have H2O, our water. Salt is made up of, like table salt, is made up of sodium chloride. So we have sodium up here, chloride over here. Sodium is positive, chloride is negative. They have an ionic bond together. And basically what happens is the more negative end of the water molecule surrounds the positive sodium ions, and the more positive end of the water molecule surrounds the negative chloride ions. So when water is surrounding each of these individually charged atoms, it's pulling them apart and actually dissolving them. So again, it's kind of attracting them like a magnet, and that's what we call a polar molecule. It's just when it's not even sharing. So it's able to dissolve solutes really, really well. And water is really good at that because of its polarity, and it can dissolve quite a few things. Not everything, but quite a few things. The second property that makes water essential for life is what we refer to as stickiness. So again, we've got our polar molecule, we've got these hydrogen bonds between opposite partial charges. So we talked about covalent bonds before. Hydrogen bonds are basically really weak bonds that form between two polar molecules. So if we've got two molecules of water, two molecules of H2O, if we want to bond them together, they'll be bonded by hydrogen bonds, which are really weak, which means that they can break and form over and over again really, really easily. Okay, so this kind of allows the water molecules to stick to one another, which means that we can have something called cohesion and we can also have adhesion. So make sure you understand the difference. Cohesion would be when water molecules stick to each other, creating what we call surface tension. So again, cohesion, I think of together, right? So it's water sticking to water, right? And then we're creating surface tension. So this can form water columns that can flow up tree trunks against gravity. You have water surfaces. I don't know if you guys have ever seen something like this, like different insects or even mosquitoes can lay their eggs on the surface of water, and that's because of surface tension, which is created by cohesion. So that's because water is sticking together essentially. So you have these things that can kind of essentially walk or land on water. Even when you see raindrops, like you'll see raindrops on you can see raindrops on water, right? You can see it kind of sticking there. But if you see raindrops on, say, a leaf, that's something that we call adhesion. So adhesion is water molecules sticking to other polar molecules that aren't water. So like adhering to it, right? So this allows water to pool on leaves or stick to an animal's tongue. If you've ever seen an animal, like say your dog or something, and you can see water droplets on its tongue, or like if you're looking at yourself when you're sweating, or if you just you're getting rained on and you can see little water droplets on your skin, that's adhesion. Okay, so that's our second property, is that water's sticky. So different things can happen there. Again, either cohesion, which is really helpful for things that can rest on water, walk on water, laying mosquito eggs, and then we have adhesion, which is where they can adhere to other water molecules. Okay, so because of these hydrogen bonds that bond the water molecules together, it means that water can stay liquid longer. So they can absorb lots of energy, meaning they can absorb a lot of heat, or energy can be a lot of different things, but a lot of times what we're talking about is heat or temperature changes. So it can absorb a lot of heat before it gets hot and vaporizes, which would turn it to a gas like water vapor, right? And they can also release a lot of energy before they get cold and solidify or turn into ice. So it means that for the most part, when you're looking at water on Earth, we see most of it as liquid water. right? We do have some ice, we do have some water vapor, but for the most part, when you see water on Earth or you're talking about water on Earth, it's liquid. And it's because it can stay liquid for so much longer based on its hydrogen bonds. So it takes a lot of energy to make it into a water vapor or to turn it into ice, which is releasing energy. So that's our last property for property number 3, why water is essential for life. Ice floats on water. Okay, and so this isn't essential for all life, right? But a lot of different life forms that rely on ice, like polar bears, for instance, which are getting into a little bit of trouble now since we have a little bit less sea ice for them. But these are the kind of things that rely on living on ice, any sort of Arctic or Antarctic animals. And basically, the way that ice can float is the density of solid water, which is ice, right? Frozen water, is less than the density of liquid water, which means that the ice is going to float on top of the water. And the reason it does that, if you look at ice, the hydrogen bonds within it are really stable. So these are weak bonds, but when they freeze, they actually hold together really well and they kind of spread apart and make it like this big raft. So think about like if you're trying to float on water. If you curl yourself up into a little ball, you're probably going to sink, or at least sink a little bit, right? Whereas if you do like a starfish and you spread your arms and legs out, you're probably going to float a little bit better. It's kind of the same thing. We're spreading out our hydrogen bonds so that we're creating kind of a wider net and we're able to float a little bit better on the water. They're also really stable, they're not breaking, whereas in liquid water, our hydrogen bonds are constantly breaking and reforming and moving all over the place. Okay. So that's the last for why our water is so important. Now we're going to get into pH. So you guys have, I'm sure, all heard of pH, and pH is basically measuring the amount of hydrogen ions that you have in a solution. So again, everything is kind of water-based. So we have water, which is H2O. So we have hydrogen and we have oxygen. So we can either have hydrogen ions or oxygen, or we can form something called hydroxide. Okay. So hydroxide is OH and it's negative. So when we talk about pH, we're measuring the amount of hydrogen ions in a solution. So when we have water molecules, our H2O, they can split briefly into either hydrogen, H plus, or hydroxide, OH negative ions. So in pure water, the number of hydrogen ions is exactly equal to the number of hydroxide ions. So our water is what we call neutral. So water that's neutral is at a pH of just about 7. Okay, so 7 is our neutral. So when we go below 7, what's happening? These are when we get into our acidic pHs, right? So when added to water, we're going to make it more acidic if we're adding acidic solutes. And that means that the number of hydrogen ions is greater than the number of hydroxide. Okay, so H plus greater than OH negative. You still have both of these present, but it means you have a lot more hydrogen ions than you do hydroxide. So acidic solution is less than 7. So these are things like coffee, orange juice, any sort of citric acid or citrus juice, battery acid, all of those things are considered really acidic. And then when we go up, if we're adding pretty basic solutes to water, then we're making it more basic. Okay, so basic can also be referred to as alkaline. If you guys have heard of that, you might be hearing about something really popular right now, which is alkaline water, which I'm happy to talk about with any of you if you're ever curious. My personal opinion on alkaline water is it's not really worth your time. If you have something like acid reflux or something like that, it could potentially make your system a little bit more basic. And basically what's happening when you're making something more basic is now your hydroxide ions are greater than your hydrogen ions. Okay, so we're moving up here. So that means that we've got a pH level greater than 7 if we're moving into something basic. So this is things like Drano is one of the most basic things you can get. It's super toxic. Ammonia, baking soda, all of those things are basic. So when we're talking about alkaline, it's the same thing as basic. If we're talking about alkaline water, The reason people think that it's really good for you is because usually acidic is not super great for you. It does a few different things to your body. So alkaline kind of has people hoping that they can make their body a little bit more of a temple, and get it to be closer to neutral slash on the slightly alkaline side. But your body is naturally not really at this level. Your body is pretty close to neutral. I think our blood pH is usually around 7.4. And most animals, including humans, most living things, can only function in a really narrow range. So keep in mind, we have to be able to maintain homeostasis. So that usually means we're maintaining our internal environment. So things like pH, temperature, we can't change too much before we would experience something really bad that could potentially lead to death. So say like temperature, right? A normal human temperature is around 98 to 99. Once you get above 99, you're kind of getting into fever territory. Once you're above 100 to 203, you're hospitalized, right? Anything above that usually is really, really bad, potentially life-threatening. Anything below that could also be life-threatening. So usually we don't want to get below, like, say 97 degrees. So we don't have a very big range of temperatures. Same with pH. Again, our blood pH, I think, is around 7.4. If your blood range goes too high or too low, whether it's too acidic or too basic, either of those things are really bad for you. So alkaline water, whatever makes you feel good, obviously do that. I don't think it's necessarily bad for you, but usually you get charged a lot for alkaline water, and it's not necessarily going to make your whole system alkaline. There's so many other things going into your body and so many other processes in your body that it's going to make basically your digestive tract potentially alkaline for a really small period of time, but it's not even enough to necessarily neutralize your stomach, which is what I think part of the push for alkaline water is. Okay. So again, pH homeostasis is very important in cells. Strong acids or bases usually are really reactive with other substances as well. So that can make them really destructive to any molecules in a cell, which means that most of the biochemical reactions can only take place at a certain pH. So you might have something that can only happen if your pH is at 7.4. If it's at 7.5, it's not going to be able to trigger itself because it would react too strongly and die or whatever it might be. So usually we've got to stay within a pretty narrow range of pH, which is what humans do too. I don't think our range is much more than like 7.2 to maybe 7.6, as far as I know. I don't think it goes much beyond that. Okay, so that's all I have for chapter 2. Again, going over what the basics of life is, going into carbon, our 4 macromolecules, as well as getting into why water is so important and what pH is, how we measure it, what it means to be basic or acidic.